Bismillahirrahmanirrahim. Assalamu alaikum students. Today our topic is Einstein's theory of the specific heat. Before discussing this theory, I want to refresh your memory with regard to the last lecture. Let me underline this. In the last lecture, we discussed the classical theory of heat capacity of a solid, in which we used the idea of law of equipartition of energy. Right? We said that if there are n atoms in a solid, then the vibrational energy of the crystal is equivalent to the energy of a system of 3n harmonic oscillators, and we took the average energy of a harmonic oscillator equal to kT, where K is Boltzmann constant and T is the absolute temperature, which in turn follows from the equipartition of energy law. Then we proved from that the heat capacity at constant volume per mole of a solid is equal to 3R, which is called Dulong-Pettit law. And when we see the value of this 3R is 5.97 kilocalories per kilomole Kelvin, right? 5.97 kilocalories per kilomole Kelvin. This is the value of 3R in this particular unit. So according to this result, heat capacity per mole of a solid is this much value, and it is independent of temperature, it's constant, which is not true in practice. The heat capacity varies with temperature. I will show you first some experimental curves. Let me draw the figure. You can draw the figure with me. Let me use another color here. This is along x-axis absolute temperature in kelvins. I will show you the approximate behavior, experimentally observed behavior of heat capacity, right? Let me complete the figure first. On this side, I have CV in the unit kilocalorie per kilomole Kelvin per kilomole Kelvin. Then use another color here. 1, 2, 3, 4, 5, and 6. This is 5 here. I'm showing these curves approximately. This curve is for carbon in the form of diamond. Then I have another curve this is for lead. Then I have another color I will use. This is for aluminium. And I will show you another one for these are approximate curves in order to give you the feel of what is happening. The first one is for lead, then I have aluminum, then I have silicon, then I have carbon in the form of diamond. On this side, I have, let me name it, this is figure 1, and it shows us what, we'll write it, variation of CV with T. T is absolute temperature, C is molar heat capacity at constant volume, right? So you can see experimentally for all the curves are varying with temperature, which is not predicted by Dulong-Pettit law. There is no temperature dependence here. It is just CV equal to 3R. At high temperatures, these three curves, red one, green one, and blue one, approach this number 5.97, kilocalorie per kilomole Kelvin, but carbon saturates at another value. At low temperatures, there's a variation in each curve of the heat, showing the heat variation of heat capacity with temperature, right? We write its absolute temperature T here. So question was before Einstein and others how to predict from theory the variation of heat capacity at with temperature at low temperatures, because at high temperature Cv equal to 3R was pretty good number for most solids, not for every solid. So to overcome the drawbacks faced by the classical theory of specific heat, there were different theories proposed by different people. So first we are going to discuss Einstein's theory of the specific heat. So let us move now to that. So a great step forward toward an understanding of the specific heat curves at low temperatures was made by Einstein in 1906. Although the physical model employed by Einstein was oversimplified, his results definitely indicated that quantum theory contained the answer to the difficulty encountered in the classical theory. Now, what he assumed, let me write that. He assumed that a solid element containing n atoms could be represented by 3n harmonic oscillators of the same frequency nu. I repeat, he assumed that a solid element containing n atoms could be represented by 3n harmonic oscillators of the same frequency nu, right? Now this model implies that the atoms vibrate independently of each other, their frequencies being the same because of their assumed identical surroundings. Now for the average energy of an oscillator, Einstein made use of a result obtained by Planck or used by Planck in 1900 in connection with the theory of black body radiation. What was that idea of Planck which was used by Einstein? According to to Planck, a harmonic oscillator does not have a continuous energy spectrum as assumed in the classical theory but can accept only energy values equal to an integer times h nu, where h is Planck's constant. As you know from your previous semesters, that this idea of quantization of energy for harmonic oscillator was used by Planck to explain the spectrum of black body. Now Einstein used the same idea to explain the specific heat of a solid. Now the Planck said that the possible energy levels, the possible energy levels of an oscillator may be represented by En is nh nu, where n is 0, 1, 2, 3, and so on. H is Planck's constant, nu is frequency. This was an important change over the classical theory. Let me name this equation. First, I have written one equation. Let me name them. In the last lecture, we have used the classical theory, where we assumed that average energy of an harmonic oscillator is kT. I name it equation 1. Then from that, we produced Dulong-Pettit law. I name this equation 2. Let me name this equation 3. Now, using this quantization idea for the energy levels of an oscillator, Planck showed that the average energy of an oscillator at a temperature T is average energy of an, we're not doing that, I'm writing it directly, you can check it. Average energy of an oscillator at a temperature T is h nu over e raised power, let me clear it, h nu over kt minus 1. Let me encircle it and name this equation as 4. So according to this quantization rule, the average energy of an oscillator at a temperature T turns out to be h nu over e raised power h nu over kt minus 1. If you compare it with the average energy of the oscillator from classical mechanics, which is kt, there is a difference. The expression for average energy according to Planck, which is equation 4, contains the frequency nu of the oscillator, right? Here there is no frequency in E equal to kt. The classical result doesn't contain any dependence of the average energy of the oscillator on the frequency, but Planck's result, and this result now used by Einstein, contains the frequency. I will draw a figure first, then I will explain. Let me draw this figure. This is figure 2. This is 1. This is 2. This is 3 yet. This is 4. This is h nu over kt. On this side I have z 5 and 1. Is it? On this side I have average energy over kt. H nu over kt, average energy kt. Let me draw the curve. What is this figure showing you? This is showing you the temperature dependence of average energy given by, let me write, the temperature dependence of average energy given by, what was this, equation 4, given by equation 4, showing average energy over kt as function of h nu over kt. where average energy is given by equation 4, right? So this is according to Planck. Note that at high temperatures, average energy is approximately kT. High temperatures means going leftwards, because when T is high, this ratio will be small. At high temperatures, you are here, this curve touches this 1 average energy over kT. That means at this point, average energy is equal to kT. So at high temperatures, the average energy given used by Einstein and given by Planck, or used by Planck also for the oscillator, at high enough temperature, this average energy is kT in agreement with the classical theory. Classical theory, remember, uses average energy for the oscillator equal to kT. So at high temperatures, there is agreement of the quantum theory with the classical theory. However, at low temperatures means you are going to the right in this graph. At low temperatures, average energy decreases exponentially to 0. At low temperatures, average energy given by equation 4, I'm talking of average energy given by equation 4. So at low temperatures, this average energy decreases exponentially to 0, right? Now let us move back to Einstein's theory. So we said now average energy of the oscillator is this one, this equation 4. Now we have to reach to the heat capacity. So in the Einstein model, the vibrational energy of a solid element containing Na atoms is thus equal to what is Na? Is Avogadro's constant. You know it. And when we take Na atoms in the solid, that means we are taking 1 mole of atoms in the solid, or 1 mole of a solid, right? So vibrational energy E is therefore per mole of the solid 3n times the average energy, 3Na. We're taking 1 mole of the solid. Why 3? You know, because I have already discussed it in the last lecture that N, the vibrational energy of a crystal containing N atoms is equivalent to the energy of a system of 3n harmonic oscillators because of 3 dimensions, oscillations in 3 dimensions. So using equation 4 for the average energy, what we get 3n times h nu over e raised power h nu over kt minus 1. We have used equation 4 for the average energy, right? This Na 3Na h nu by e raised power h nu by kt minus 1. Let me encircle it. And name it as equation 5. This is 4. Now this is my equation 5. Right? Therefore, the heat capacity per mole at constant volume is heat capacity per mole at constant volume, which we represent by CV. Heat capacity per mole at constant volume CV is, remember, CV is the partial derivative of this energy E, the temperature, and using equation 5 for E, I will write directly. It is 3R times h nu by kt square e raised power h nu by kt over e raised power h nu by kt minus 1 square. What we have done, we have used 5 for equation 5 for E. So I write using equation 5. So let me encircle it. And name it. This is my equation 6. This was 5 for E. Let me check it. CV is partial derivative of the energy E with temperature, which turns out to be 3R times h nu by kt square times e raised power h nu by kt over e raised power h nu by kt minus 1 square. Right? So I will give you homework. Check it at home. What you have to do, you have to simply differentiate this E with temperature to get CV, and you check that you get this expression. This is your home assignment. Now, before discussing this result, it may be remarked, there's a remark. What is the remark? According to quantum mechanics, or I will use green color, according to quantum mechanics, the possible energy levels, the possible energy levels of a harmonic oscillator are given by let me move to the next page. En is equal to n plus half h nu. H is Planck's constant, nu is frequency, where n is 0, 1, 2, and so on. Let me encircle this equation and name it as equation 7. Rather than which equation we used, rather than 3, right? I repeat, according to quantum mechanics, the possible energy levels of a harmonic oscillator are given by this rather than En is equal to nh nu, where n is 0, 1, 2, 3, and so on, which is our equation. Which equation? Equation 3. Right? What will, if we use this energy expression, will it affect the expression for energy? It will affect the expression for energy. You can check it at home, one more home assignment, but it will not affect CV. Why so? I will tell you. What will happen? This has the effect of shifting all energy levels by the constant amount of h nu by 2. Let me write. This has the effect of shifting all energy levels by the constant amount h nu by 2, constant amount of h nu by 2, and instead of, what is this equation? 4. Instead of equation 4, one obtains average energy of the oscillator as h nu by 2 plus h nu over e raised power h nu over kt minus 1. Let me encircle it and name it as equation 8. So if you use this result for the energies of a harmonic oscillator, you will get average energy of the oscillator as given by equation 8, which is h nu by 2 plus h nu by e raised by h nu by kt minus 1. Instead of the average energy obtained as h nu over e raised by h nu by kt minus 1, that is equation 4, right? But that will not affect the expression for CV, because when you differentiate this energy with respect to temperature, right? This average energy, to get the total energy, you have to then multiply by 3 Na. If you take 1 mole of the substance, when you multiply it by 3 Na, what will happen to this average energy? You will have one more additional term in the sum, which is 3 Na h nu by 2, right? Rest is same. This term will be same. 3 Na h nu by e raised by h nu by kt minus 1. And when you find then heat capacity per mole at constant volume, you will differentiate the expression of the energy with respect to temperature partially. This term, which will be constant, that will vanish to 0, and you will get the same expression for CV as equation 6, right? Now this first term, h nu by 2, this term has a name. The first term is called the 0-point energy of the oscillator, because average energy is equal to h nu by 2 for t equal to 0. This will be called h nu by 2 for t equal to 0. Thus, according to quantum mechanics, the atoms have vibrational energy even at absolute 0. As I already said, the expression for the specific heat is not altered by this result, because CV is determined by the derivative of energy with respect to temperature T. So this expression will not change, right? Now, with regard to equation 6, that is the expression for CV, it is observed that for KT much greater than h nu, let me write it. This was a remark. Now we move to the main thing with this was a remark from this to this. Now we move to the main topic. This is all main, but I want you to be clear. Now with regard to equation 6, it is observed that for KT greater than, very greater than H nu. That means at high temperatures, this expression, equation 6 for CV reduces in first approximation to the classical result. Which is our classical result? Dulong-Pettit law. I have named that equation. Equation 2. This is my classical result. Equation 2, Dulong-Pettit law. As is indicated by the curves which we at high temperatures, Dulong-Pettit law is obeyed by most solids, right? This equation is at right track, right? At low temperatures, however, this was at high temperatures. At low temperatures, however, as we have seen in the curves, the specific heat decreases. Right? Now, to discuss this behavior at low temperatures, it is convenient to discuss this low temperature behavior. This behavior, it is convenient to introduce the Einstein temperature theta subscript E defined by H nu is equal to K theta E. That means theta E is H nu over K. This is the defining equation for Einstein temperature. Let me encircle it and name it. This is our equation 9. Right? Now, equation 6, that is our expression for heat capacity, CV, may be written in the form, may then be written in the form. We use the definition of Einstein temperature from 9 to re-express the expression for CV. Simply we replace H nu by K h nu by k by theta e, h nu by k here by theta, h nu by k by theta e, right? So what we get? Write it this way, CV over 3R is equal to theta E over T square. Let me use another color. E raised power theta E by T, E raised power theta E by T minus 1 square. Let me check it. CV by 3R is theta E by T square times E raised power theta E by T over E raised power theta E by T minus 1 square, which we write as FE theta E over T. Let me name it equation 10. I will encircle it first. Name it equation 10, where FE is called the Einstein function. What does this Einstein function do? It gives you CV by 3R ratio. That means it determines the ratio of the molar heat capacity at constant volume classical result. It gives you ratio of that to the classical result of 3R, ratio of CV by 3R. I will show you the graph of Einstein function. Approximately on this side you have theta T over theta E. On this side we have the Einstein function FE theta E by T. Let me draw this function. This is 0.2, 0.4, 0.6, 8, 1, 1.2. This one here. 1.2, 1.4, 1.6. Then I have 1.8 and 2. On this side, let me use another color. I have 0.2, 0.4, 0.6, 0.8, 1. Let me use another color. This is the graph of the Einstein function as function of T over theta E. Let me name it figure, I think figure 3. What is, we have shown some figure. This was figure 2. This is figure 3. Let me give you the understanding of this figure. The Einstein function is represented in this figure 3 as you are seeing it. We see that the curve obtained has the same appearance as the observed specific heat curves. Compare this curve with the specific heat curves. These are the specific heat curves obtained experimentally for different elements. You can see the shape of the curves matches with the Einstein function, right? But there is a problem with this curve. What is the problem? The Einstein curve deviates from the experimentally observed ones in the region of low temperature. Let me write it. This is important. The Einstein curve deviates from the experimentally observed ones in the region of low temperatures. Need to remember it. Experimentally it is found that for most solids, the lattice specific heat at very low temperatures for example, if you take liquid helium, is proportional to when I say liquid helium, it means those low temperatures at which liquid helium exists that means at very low temperatures. The that specific heat of most solids is proportional to T cube. T is the absolute temperature. However, for T much less than theta E, Einstein temperature, that is low temperatures, equation, what is the name of this equation for Einstein function? Equation 10. Equation 10 leads to a specific heat proportional to exponential minus theta E over T, not proportional to T cube, but proportional to exponential of minus theta E by T. What does that mean? That means Einstein's functions falls off more rapidly at low temperatures than it should. I should write it. In other words, the Einstein function falls off more rapidly at low temperatures than it should. I repeat, the Einstein's function falls off more rapidly at low temperatures than it should. So there is a discrepancy. That means the Einstein's theory of specific heat for solids is not the whole story. The reason for this discrepancy must be sought in the oversimplified model implied by Einstein. I hope you got the point. You have got this theory into your mind and heart. This is all for today. Go through all the video lectures. Don't waste your time. Learn at your pace. You can make notes out of it using these video lectures as well. And don't forget to subscribe and like my channel. You can also comment. Thank you. God bless you. Assalamu alaikum.